Great, thank you very much for the presentation. I believe in addition to Yang, I believe some of the co-authors on the paper are also available to answer questions. Why don't I start us off with a question? So one of the common problems with speculative execution is that there's significant overhead for mispredictions. Can you comment on how much overhead you saw when your modified Ethereum node was running on mainnet? Sorry, you might be muted. Yang?
Oh,
I believe you're muted. Or perhaps your mic is just not working. Perhaps one of your co-authors might be able to answer this while we try to fix your mic. Hi, Chen.
Oh.
I think.
Hello. Yeah.
Would you like to answer the question? Do you want me to repeat it?
Oh yeah. Yes, please.
Sure, I can do that. So
Yep.
what I was saying before is that a common problem with speculative execution is that it introduces overhead, especially when there's mispredictions. And I just wanted to ask you if you can comment on how much overhead you saw when you were running Ethereum on mainnet, your modified version of Ethereum node on mainnet.
Yeah. So I think the misprediction. Let me share the slide first. All right. Okay. Oh, I can't share the I can't share the screen. So what happened here is that if we mispredict, then the overhead is the pre-execution, which is to first it is to construct the AP program. So our real data shows that even with this kind of overhead, we are able to quickly within the time budget, we are able to do all the we are able to finish these pre-executions within the time. So, but at this point, I don't have the exact number, but perhaps Yang, I don't think we reported the number in the paper. Do you have any remember any number that you can remember about this exact overhead? I'm sorry, I don't have the exact number.
Oh, no, that's fine. Yeah, so I just trying to get a sense of how much overhead, and I guess the reason for this question is that my worry is that the computational requirement will increase, and this might reduce decentralization, since fewer nodes would have enough processing power to participate in the network. So that was really what I was trying to get to, like, if it requires more resources to participate, is that going to cause issues in terms of getting?
Oh yeah. So related to this point, I think a great thing about doing speculative execution for Ethereum is that we can use if we find out that the resource is not sufficient, we can always increase the machine power, the machine resources, in order to do more pre-executions, right? Because we are now no longer constrained by the sequential semantics of the execution. In fact, what we do is to utilize the multi-core of the system so that we can do concurrent executions. So in this sense, we are freed from the constraints in the execution phase. We are able to fully utilize the machine power in parallel.
Great, thank you very much. Yeah, I think that answers my question. I think we have a live question from Sudan.
Oh.
Yes. So if I understand correctly, like the definition of CD equivalence is really based on the trees. So you need to have the trees of two features to tell whether they are CD equivalent. So my question is that let's say you have pre-execute feature Y, and then in like reality you found it's actually feature X. But without executing X, how do you know that X is actually CD equivalent to Y? Because you don't have the trace of X, Y. So that's basically my question.
Okay. So your question is so execution Y is the actual execution, and execution X is the pre-execution, right? So your question is, without executing without doing the actual execution, how do you know they are equivalent? That is a very good question. It's that is where the concept of constraints comes in. So when we pre-execute the trace X, we actually come up with the CD equivalence constraints. This is a set of constraints. So the magic here is that when the time comes for the actual execution, we simply check these logic constraints. If they match, that means they are equivalent. That is really the key. Once they are equivalent, we know that we can borrow the pre-execution result. And then by doing a lot of PL optimization techniques, we are able to run the chase really fast. Yeah, that's I don't know whether I answer your question.
Yes, and I have a follow-up question. So you mentioned the constraint set, right? So is this constraint set actually 100% accurate? That is, as long as you satisfy the constraint set, these two executions should be definitely CD equivalent. And also, if you do not satisfy the constraint, they should not be CD equivalent. So, like, is that the case, or there could be some like missing?
No, the logic constraints are accurate.
Accurate.
Yeah, okay. They are accurate, and this accuracy is important. Otherwise, we would not be correct. And about the correctness, a really good thing about this work is that we run like for 10 days the live traffic of Ethereum, and you know that as long as if we made any mistake during the calculation, it will be caught by a Merkle root, right? So as long as we made any mistake, it will be very obvious. But in our case, we run the entire 10-day chase, and our Merkle roots always match the official ones.
I see.
Yeah,
that's impressive. Thank you.
Yeah. Sure.
All right. Do we have any more questions for Rohan, I believe, has his hands up.
Hello, hi. So I'm
Hi,
not
hi.
very well versed with Ethereum, but my question is that you mentioned before that you can like get more resources if you fall short of resources during pre-execution. But my question was in terms of like resource efficiency. So can you like if you have to waste many resources, can you instead use like more conservative resources? Like what is the wastage in some sense?
Oh, okay. So I think you are asking about the overall resources that we consume to do the pre-execution. So
Yeah.
in the paper we have this number, but let me get the number for you. So the overhead is yeah, I think we report a number which is 12.19 times more resources than the actual execution. So so yeah, but it's important to recognize that this is during the pre-execution, then and essentially we can throw more resources into this phase without worrying about the sequential semantics of the execution. So this is like that is the number we report. But I think it's the benefit is that during the pre-execution phase, we do all the work. Then once the real execution starts, then it will be very fast. That's the thing. And also an additional point is that the ultimate goal of this acceleration is that we are able, we hope that this technology is able to open the opportunities for throughput increase for Ethereum's layer 1.
I see. Okay. So in the critical path, you don't need to use up those resources. You use them during pre-execution, and that is why it is a good. It is a reasonable thing. Okay,
yes, yes, exactly. So if we didn't do the pre-execution, then you can imagine that even if you have a supercomputer, you have to wait. You can't do anything until the real execution starts, right? Yeah.
Okay, thank you.
So, okay. One more thing is that at this point we of course only focus on the acceleration during the actual execution. So we hope that with further effort to optimize the pre-execution, then the overhead can be lowered. But that has not been our focus up to this point. It is possible.
Okay, thanks.
Yeah, sure. Thank you.
All right, thank you very much. I think that's all the time we have for this session. So thanks again to all the presenters. And I think if you have any additional questions for any of the authors, you can leave them on Slack. I'm sure they'll be happy to answer them. And after the break, I believe we have session 13 on scheduling. You guys.
Thank you.
Okay, great. It looks like we have Xian with his hand raised. Do we have the authors all here? Let's see. Did someone promote the authors?
Yes, I think all my co-authors are already been promoted.
Okay, great, perfect. Yeah, Xian, why don't you go ahead and ask your question?
Okay, so
Perfect.
hello, I'm a PhD student from Hong Kong University. So first, thank you for the great talk. So my question is about in terms of using spatialization to accelerate simulated executions. I wonder if Forerunner can even achieve better performance from other hints. For example, when transactions could share a common subset. Thank you.
Sorry, could you repeat the last part of?
I wonder if Forerunner can achieve a better performance from other hints. For example, when a transaction input could share a common subset.
So are you talking about something like other than the blockchain?
I think I actually had this question as well. Maybe put a different way, would you be able to achieve better performance if you understood the dependency between the operations that you're speculating over? Does that make sense?
Yeah.
Yes, I think maybe let me first answer Tian Xiang's question directly. I think our shortcut mechanism is exactly for the purpose of to leverage the shared common subsets of input values to further acceleration. So that's what the shortcut is for. So basically, our shortcuts can automatically detect whether they have a common subset of inputs. If so, the AP execution, the corresponding AP execution will be skipped. So that will make it even faster.
Yeah. So actually, let me try to give some maybe high level answer. If the question is whether the idea of constraint-based speculative execution can be applied to other areas than blockchain, I think that this is a very interesting thing. So in fact, a lot of our insights came from our earlier studies about real Ethereum transactions. So we had fairly good understanding about their characteristics before we started the Forerunner project. So in this sense, yes, blockchains seem to be a niche for us. But this being said, we do feel that constraint-based speculative execution is an insightful idea of its own. So we do hope that there are other very nice niches to be found to apply this great idea, because the essence of the idea is that when we do speculative execution, we don't need to based on concrete values. We based on logic constraints, and we can match based on equivalent classes rather than like each and every concrete instances, right? That is really the key. I don't know whether I answered that question.
Yeah, thank you. Thank you for the answer. Yes, I got it.
Yeah, I think one question that I had in particular, actually, let me let G ask his question, and I'll save my question for for the end if we have time.
Okay, thanks. Thanks for the great talk. I'm Jay from Hong Kong U. I have several short questions. The first question is, can program analysis capture all the possible future contexts? In other words, what kind of transactions can Forerunner support? Can you support all kinds of transactions or all kinds of operations?
Yes, it can support all the full EVM semantics. Any smart contracts can be supported.
Yeah. So again, I also want to add one more point. So so our evaluation, although you may see that as a performance evaluation, as a byproduct, actually we validate with super high confidence about our correctness. The reason is that we have processed like for 10 days 13 million transactions, which generate 66,000 blocks, and for each and every block our Merkle root has to match the actual correct Merkle root. So if we made any single bit mistake, we will be caught, right? So the fact that we can do this evaluation is actually a very high confidence validation of our correctness. So we did correctly process all the transactions that we encountered.
Okay, thanks. Another short question. So how many future contacts are there for each transaction on average? So is it possible for a very complex smart contract, there may exist a large number of future contacts, and you need to prepare a lot in the pre-execution phase?
Yes, and I think we have achieved this 98% of like speculation success rate. So there are still less than 2% of the transactions that we currently cannot handle, and that's exactly because those transactions have too many futures, or maybe more precisely, they have too many CD equivalent classes. So that even if we already try to have multiple fast passes for them to cover as large as the space as possible, we still like fail to accelerate them. So yes, there are still a small percentage of transactions that have too many futures for us.
Okay,
so that's a part that we can continue work on.
Okay, very appreciated.
So a short additional point is that when you said the number of futures, in fact, in our case, that is translated into the number of equivalent classes, right? So that is the power of our technique. We don't treat every future as an instance. We treat them as equivalent classes. So what really matters is how many equivalent classes that we need to deal with.
Okay, thanks. Yeah. That makes sense.
Yeah.